In this video, we're going to talk about concentration of solutions and how to find the concentration. All right, so we know that reactions take place here when we mix two solutions. Oftentimes we get a precipitate forming, and that tells us that a reaction took place. But in order to do anything here with stoic, we're going to need to know the concentration of these solutions. All right, so concentration is just talking about the amount of solute that's in a specific solution. So the amount of the solute is important here. That's going to relate here to this idea of concentration. If you know the concentration, you can do stoichiometry with these things. But there's a few different ways to express concentration, and I'm only really going to show you two of them in this video. The biggest way to express concentration is called molarity. It gets denoted with a capital M. All right. Molarity is the moles of solute per liter of solution. You really have to understand what molarity means here in order to be able to do these problems. All right. So anytime you see a capital M, that's the same thing as saying moles of solute over the liters of solution. So when you divide the moles of solute by liters of solution, you get the molarity or the concentration. If a problem just says find the concentration, by default, you just find the molarity here. All right, there are other forms of concentration, but the default one for us is going to be molarity, moles of solute per liter of solution. I want to jump right in and look at an example, and I have it solved out for you so you can see this. So this problem says calculate the molarity of a solution when 11.5 grams of NaOH is dissolved in enough water to make 1.5 liters of solution. All right, so they want to know the molarity. They're telling you, find the molarity. In your head, you should be saying, okay, I know molarity is moles over liters, moles of solute over liters of solution. So if they want you to find the molarity, you need to set your problem up with something over something. All right. In this problem, I can see that they gave me the grams of NaOH and they gave me the liters of solution. So in order to do molarity, I need moles over liters, but I don't have moles, but I do have liters. So I picked a number that I could use on top to get me to moles. So I put the 11.5 grams of NaOH on top. That's going to be my solute here. So you do have to think about this sometimes. The solute is what's going to be dissolved here, and the solvent is doing the dissolving to make the solution. So the water is going to be the solvent here to make your solution. So I put the 11.5 grams of NaOH on top all over the 1.5 liters of the solution. Remember, my goal here in order to get molarity is moles of solute over liters of solution. Right now, if I just solved this, I would have grams per liter. That's not what I want. I need moles per liter. So you have to convert here. You put your multiplication symbol, put your conversion line. The liters is good on the bottom, so I don't need to worry about that. I just need to get rid of the grams and get that to moles. So my grams of NaOH on top, I immediately write it on the bottom. You have to find the molar mass of NaOH. There's 40 grams of NaOH for every 1 mole of NaOH. So remember, do your molar mass calculation and show it. I'm just trying to save a little time here. You do have to show your molar mass. Your grams cancel, and now if you check here, you have moles of NaOH on top over liters of the solution on the bottom. Those units don't cancel. Moles over liters is a definition of molarity. So now you just plug and chug, solve, watch your sig figs, and it comes out to be 0.19 capital M, or 0.19 molar. Because you had moles over liters, that's the same thing as saying capital M. You could write moles divided by liters, but you got to get used to seeing it as capital M. You just need to know that capital M is the same thing as moles over liters. That's molarity. We can try another problem here. So this example says how many liters of 4.0 molar solution can be made using 125 grams of LIBR. So we're trying to figure out how many liters. All right, this problem is not asking us to find the molarity or find the concentration like the previous example. Whenever you're asked to find the concentration or find the molarity, you set the problem up with something over something because you know you need to get moles over liters to get molarity. But when you see a problem like this, when you're given the molarity and another number, there's kind of a trick here with all these. Anytime you're given the molarity and another number, all right, you start with the other number and you use the molarity along the way in part of your kind of conversion here. All right. So if you're not solving for the molarity, you're given the molarity and another number, use the other number, and then the molarity is used in your problem as part of the dimensional analysis here. So I'm going to start with not the molarity, the other number, the 125 grams here of the LIBR. The labels are not necessarily super important for the molarity calculations because you're not switching substances. We're not doing stoic yet. But some problems, I include them if it helps me remember what the substance is. So I have to start with the grams. I have to put my multiplication symbol in my conversion line here. I know the grams of LIBR go on the bottom. Remember, you're going to have to use this molarity number in the problem. Well, molarity is the same thing as moles over liters. So I either have to somehow get these grams to moles, or if you could get the grams to liters, but you can't. You got to get to moles here so that you can use that molarity. Grams would go to moles. So we know for every 1 mole of LIBR, there's going to be a molar mass of this. All right, so this one's pretty easy. We can show this. There's 1 Li times 7 each is 7. There's 1 Br times 80 is going to be 80. And we got 87 grams per mole. So there's 87 grams of LIBR for every 1 mole of LIBR. Now you're in moles. Now you can use your molarity. Remember, you're going to have to use this molarity along the way. It's the only way you can get this to liters. So you put your multiplication symbol, you put your conversion line. You know moles of LIBR have to go on the bottom in order to get your units to cancel here. All right? But how does this actually work? Well, remember, what this is saying right here is that there's 4.0 molar is the same thing as saying 4.0 moles per liter. So there's 4.0 moles of LIBR for every liter. That's the same thing as saying 4.0 capital M. And yes, the moles go on the bottom here, and the number always goes with the mole. Remember, if you were saying, 4.0 molar, that's the same thing as saying 4.0 moles for every liter. All right, and the moles were on the bottom. That's the only way they cancel. So the number and the moles go on the bottom. But now you're in liters on top. Well, the question says, how many liters? You're done. So you see how we started with the grams and we used the molarity along the way. We just needed to know that molarity means moles over liters. So now when you plug and chug and sig fig this, we're only going to have 2 sig figs. It's going to be 0.36 liters with correct sig figs and units. All right, so that's just kind of a different variation here of a molarity problem where you're using the molarity and not solving for the molarity. This problem wants to know what mass of oxalic acid, and they gave you the formula of oxalic acid, is needed to make 250 milliliters of a 0.0500 molar solution. All right, so this problem, again, does not say find the molarity or find the concentration. So I'm not going to set the problem up as something divided by something. I'm going to start with the number that's not molarity and then use the molarity along the way. Whenever you're given molarity in another number, you start with the other number. So I'm going to start this problem with the 250.0 milliliters. All right. I know I'm going to have to use the molarity here. I know molarity means moles over liters. So I have to convert these milliliters to something that can get me to one of those units, either moles or liters. Well, if you're ever starting with milliliters, you know milliliters have to go on the bottom. The only thing you can get milliliters to here that you can use is liters. We know that there's 1,000 milliliters for every 1 liter. Now that you're in liters, now you can use your molarity. We know that the liter has to go on the bottom in order for them to cancel. And we know from the problem here that there's 0.0500 moles for every liter. Okay, by writing 0.0500 moles over liter, that's the same thing as saying 0.0500 capital M, because capital M means moles over liters. Your liters cancel, and right now you're in moles. Well, we want to know the mass, so you just keep going here. We know that for every 1 mole of oxalic acid, there's going to be a certain number of grams of this. All right, and then to save you time here, I'll do the molar mass, and when you do calculate it, it does come out to be 90 grams. Remember, show your molar mass in these problems to get full credit. Your moles will cancel here, all right, and then you're in grams of the oxalic acid. So you just need to plug, chug, and watch your sig figs. This one's only going to have 3 sig figs, all right, because of the molarity there. So it should come out to be 1.12 grams with correct units and sig figs. So this was another example of where you had a number and a molarity, and you start with the number and use the molarity along the way. We were not finding the concentration, we were using it. You got to remember molarity means moles over liters. One more example to try here. It's saying what is the concentration of a solution that has a volume of 2.5 liters and contains 660 grams of calcium phosphate. So notice in this problem, it's asking what is the concentration. That's the same thing as asking what is the molarity. So I'm looking for molarity here. I know molarity means moles over liters. So I have to set the problem up as something divided by something. All right, so that's how I'm going to have to set the problem up because I need to get concentration or molarity here. So the only numbers they gave me were 660 grams and 2.5 liters. Obviously, if molarity is moles over liters, the liters have to go on the bottom. That makes it really easy. And unfortunately, I don't have moles, but I have a number that I can get to moles on the top. I have the grams. I have the 660 grams. All right, so I can convert here to get moles over liters. Right now I'm in grams per liter. That's not molarity. So you're gonna have to convert. Your liters on the bottom are good. All right, you could easily have, milliliters and have to convert them to liters on the bottom as well. You just do two kind of dimensional analysis problems here. And some people do that. They'll do two separate dimensional analysis problem and just divide the numbers at the end. That works too, but I sometimes like to just do it in one kind of swoop here. So I know that the grams have to go on the bottom to get rid of them. Again, when you do the molar mass here of this compound, I'll save you time. It does come out to be 310 grams for every 1 mole. Remember, you do need to show your molar masses. Grams on top and grams on bottom, so they're going to cancel. Your only units you're left with here are moles over liters, which is the definition of molarity. So when you plug, chug, and sig fig this, you're only going to have two sig figs. It should be 0.85 capital M, or 0.85 molar. It's the same thing as saying, it's the same thing as if you wrote 0.85 moles divided by liters. It's the exact same thing, but you need to know that capital M means moles over liters. It's a form of concentration. I want to show you another type of concentration here called molality. I know it's very similar to molarity, but it's something different. We denote this with a lowercase m, and technically that m is even like italicized because it's not a meter. All right, similar definition here, but obviously it's different. Molality is going to be the moles of solute per kilogram of solvent. So the moles of solute part on top is the same, but the kilogram of solvent on the bottom is different. In molarity, we were looking at the entire liters of solution on the bottom. Here, we're looking at the mass of the solvent itself. So just pay attention here. In order to do these problems, you have to pay attention to what's the solute and what's the solvent, because they might give you the mass of each. So you have to pay attention to what's actually dissolving, all right? What's being dissolved, that's the solute, and then what's doing the dissolving, that's the solvent. So I showed you this example here just so you could see it. I'm not going to go totally in depth and do examples, but I want you to at least see this one. It says, in lab, 1 mole of C2H6O2 is dissolved in 250 grams of water, and you want to calculate the molality. So in your head, you'd be saying, okay, I know molality is moles of solute per kilogram of solvent. They want me to find the molality, so I have to set the problem up as something divided by something. So you have to be careful here. Which one's the solute, which one's the solvent? Well, they told you were dealing with water, so you pretty much know that the water is going to be the solvent in these problems, all right? So we'll put the 1.0 moles on top, and we'll put that over the 250 grams of water on the bottom. The water is the solvent, and the C2H6O2 is your solute. So in order to do molality, you need moles of solute over kilograms of solvent. Right now, you'd be in moles per gram. So the moles are good. You just need to get the grams on the bottom to become kilograms. So you put your multiplication symbol, you put your conversion line. All right, we want to cancel a unit that's on the bottom, so we write it on the top. All right, so grams of water on top. In order to get the kilograms, we know there's 1,000 grams for every 1 kilogram. So when your grams cancel, your only units that are left are moles over kilograms. And that's the definition of molality. So when you calculate this in sig fig, you get 4.0 little m. It's the same thing as saying 4.0 molal. I know that sounds weird, but that's molality. This is used in some different types of problems. Typically, molarity is the big form of concentration that we use, but I just wanted you to at least see molality here and know what it means. Before we're done with this video, I want to talk about the proper way to make a solution because this is very important. This is important lab skills that you definitely need. All right. In order to make a specific concentration, like let's just say you wanted to make a 1 molar solution of something, say 1 molar solution of salt water. Okay, there's a specific set of steps you need to follow. So the first thing it says here is that the solid should be weighed out first and then placed in a volumetric flask. This is what a volumetric flask looks like. All right, it has usually one line on it and it's calibrated to the exact volume. So if this was, say, a 500 milliliter volumetric flask, that line would be exactly 500 milliliters of solution. Okay, so when you hit that line with your liquid, you know that there's exactly 500 milliliters of solution. So what you would do first is if you wanted to make a specific concentration of a solution, you measure out the amount of solid you need first, you put it in the volumetric flask, and then you add some of your solvent. So if you're going to probably use water, you add some water to this. Notice it's not filled up. You add some water to it and then you dissolve it. Okay, and then once your solute is dissolved, then you fill up with water to the line. All right, this means you have exactly, say, 500 milliliters of solution at the specific concentration you wanted. If you put the solute in and then added all the water up to the line, when the solute dissolved, the liquid level would rise above that specific line. So say above 500 milliliters, and then you no longer have 500 milliliters of solution. So you have to dissolve the solute first and then add the rest of the liquid up to the line. If you were making Kool-Aid, in theory, you dump your powder and your sugar in, you add some of the water, dissolve it, and then fill up to the line on the container. Otherwise, you're making a weaker form of Kool-Aid. This is the proper way to make a solution, and you need to get used to the materials. This is called a volumetric flask. A lot of times here, in order to save space, time, money, we buy prepared or concentrated solutions, which basically means when we're purchasing acid, say for example, hydrochloric acid, we usually buy 12 molar acid, 12 molar hydrochloric acid. I don't always need 12 molar hydrochloric acid. A lot of labs we might use 1 molar hydrochloric acid, maybe 3 molar hydrochloric acid or 6 molar hydrochloric acid. So the key is we buy a very concentrated form of hydrochloric acid, which doesn't take up much space. And then we add water to dilute the stock solution to get the desired concentration here. So I take a certain amount of the 12 molar, add a certain amount of water, and then I can get 1 molar hydrochloric acid. The key is when you do these dilutions, the moles of solute before equal the moles of solute after. Okay, you're not adding solute here during a dilution. You're just adding water. All right, so because of this, you can do a pretty easy calculation here since the solute is staying the same. So you can actually calculate how much water would need to be added and figure out the volumes and the molarities here as we're going to see for these dilution problems. In order to do a dilution, you're going to use this simple equation right here. MV equals MV. You have a beginning molarity and volume and an ending molarity and volume. And your units don't necessarily matter here for volume as long as they match. If you're using liters on one side, then you're going to have liters on the other. The key is these are a dilution problem because you have multiple molarities or multiple volumes or you're adding water. So you have to look out for some of these clues when you're doing some of these molarity or concentration problems. You have to realize that you're adding water. That's usually a dead giveaway that you're doing a dilution. All right, or it might say something about stock solution or something like that. So if you look at the example here, it says what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.10 molar solution. Okay, so you can see I have multiple molarities here. I have one volume and I'm looking for a volume, that's a dead giveaway that this is a dilution problem. So it doesn't even matter which side things are on. The key is you pick a molarity and you start. I have 16 molar as my concentration here. And according to the problem, I want to know what volume of that I need. So that's going to be my unknown here. And I'm going to set that equal to my other molarity, 0.10 molar, and my final volume that I want to end up with, 1.5 liters. So essentially what we're trying to do is we're trying to take a super concentrated amount of sulfuric acid, a certain amount of it that we don't know, and we're trying to get it to be diluted or weaken it down to 0.10 molar. All right, but we only want 1.5 liters of that. So all you do now is solve for your unknown here. Okay, do your math, solve for the unknown, and it comes out to be about 0.0094 liters. Remember, if your volume is in liters on this side, this volume is going to spit out liters. So I just converted that to milliliters just so you could see a nicer number. It's about 9.4 milliliters. So what some people think is, oh, if I just measure out 9.4 milliliters of 16 molar sulfuric acid, I now have 0.1 molar. No, the only way you get it to be 0.1 molar is if you add water. Okay, so this is telling you the amount of the 16 molar sulfuric that you need. Well, how do you get it up to 1.5 liters or 1500 milliliters? The rest has to be water. Okay, so essentially, if you take 9.4 milliliters of the super concentrated sulfuric and you add to that 1490.6 milliliters of water, that will give you your total of 1.5 liters or 1500 milliliters, and then that will dilute 16 molar down to 0.1 molar. So you have to be careful what the problem is asking. In this case, it just asked what volume of the 16 molar do you need? So it would just be this answer. But if the problem said how much water do you need to add, it would be this answer. So you got to be very careful in these dilution problems and just make sure you pay attention to what the problem is asking. We can try an example here of one of these dilution problems. It says how many milliliters of stock solution should be used to prepare 300 milliliters of 0.750 molar NaBr solution using 2.00 molar stock solution. Okay, so I can see in this problem I have multiple molarities. I'm given a volume. I'm asked to find for a volume. They're talking about stock solution. These are kind of some dead giveaways that this is going to be a dilution problem, and I have to use MV equals MV. All right, so pick a molarity and start. The first molarity I see is the 0.750 molar. All right, the volume that goes with that, it tells me that I'm trying to prepare 300 milliliters of that. Okay, I'm going to set that equal to my other molarity. I am given the 2.00 molar. Okay, and I want to know what volume of that or how many milliliters I should be using of the 2 molar to prepare 300 milliliters at 0.750 molar. So you have to solve for your volume here. When you plug and chug and solve for V, it should come out to be 112 milliliters. Remember, your units here are going to match the other side. So that would be the volume of the 2 molar stock solution that I need in order to eventually get this to be 0.750 molar. It did not ask me how much water. If I wanted to know how much water here, I'd have to see I'm trying to make 300 milliliters and I need 112 milliliters. So the difference between them would be the amount of water that you need to add. So this is just another example of a dilution problem using MV equals MV.